If our protons rotated around in sync, in phase, and nothing changed, then we'd get a signal as illustrated in the previous section. This, however, is not what happens. This is the situation right after the RF pulse was switched on. As soon as the RF pulse is switched off, the whole system, which was disturbed by the RF pulse, goes back to its original, quiet, peaceful state. It relaxes. The newly established transverse magnetization starts to disappear, a process called transversal relaxation. And the longitudinal magnetization grows back to its original size, a process called longitudinal relaxation. Why is that? The reason why the longitudinal magnetization grows back to its normal size is easier to explain, so let's start with that. No proton walks on its hands longer than it has to. A sort of human trait. The protons that were lifted onto a higher energy level by the RF pulse go back to their lower energy level and start to walk on their feet again. Let's have a closer look at what happens. Sending in the RF pulse makes, let's say, 3 protons walk on their hands. Note that for simplicity, the protons were not depicted as being in phase. This subject is covered in more detail in sections 12 and 16. After the RF pulse is switched off, protons go back to the lower state of energy. In other words, point up again. But not all protons do this at exactly the same time. Instead, it is a continuous process, as if one proton after the other goes back to its original state. The effect is that longitudinal magnetization increases and grows back to its original value. What happens to the energy which they'd picked up from the RF pulse? The energy is just handed over to their surroundings, the so-called lattice. And this is why this process is not only called longitudinal relaxation, but also spin lattice relaxation. If you plot longitudinal magnetization versus time after the RF pulse is switched off, you get a curve like this one. It increases with time. This curve is also called a T1 curve. The time that it takes for the longitudinal magnetization to recover, to go back to its original value, is described by the longitudinal relaxation time, also called T1. This actually is not the exact time it takes, but a time constant, describing how fast this process goes. This is like taking time for a circuit at a car race. The time gives you an idea of how long the race may take, but not the exact time. Or more scientifically, T1 is a time constant comparable to the time constants that, for example, describe radioactive decay. That T1 is the longitudinal relaxation time can easily be remembered. If you turn the 1 upside down, it looks very much like an L, as in longitudinal, reminding you also that it describes the spin lattice relaxation. But there are more hidden hints to this. The 1 also looks like a match, and this match should remind you of something which we've also mentioned already. Longitudinal relaxation has something to do with exchange of energy, thermal energy. which the protons emit to the surrounding lattice while returning to their lower state of energy. Enough of the longitudinal magnetization. What happens with the transversal magnetization?